Hello, everybody, and welcome to this week's Rising Tide Foundation lecture. A couple of weeks ago, we rounded out a 3 month long symposium on the theme of science unshackled. And it was a lot of fun, and there was a little bit of an epilogue, which has been floating around waiting to be stated. And a lot of the scientific material that we had looked at dealing with cutting edge work that has been either suppressed or derailed has touched upon. We had presentations on geology, earthquake science, quantum mechanics, everything from above and below, and life science and everything else. It was a lot of fun, but we didn't deal with a lot of the dynamics of the historical content of science from the standpoint of universal history. So I was really looking forward. Cynthia, myself, Kevin, Pascal, we've been having some conversations on how to best maybe sort of wrap up that package by treating both elements. And as I think everybody here has gotten a sense of by having been through the Rise and Tide Foundation lecture series, we really do try to focus on the question of the science of history, looking at history as if it has actual causal principles organizing the empirical data, which can be measured in a certain extent on timelines. You can look at dates, you can look at the events in the material realm, but really, we want to really get at this question that was developed by Schiller, by people like Lyndon LaRouche, by many others throughout history, that there's causal agencies located in the domain of intention, the domain of ideas, both ideas that are true, founded upon natural law, and the disobedience, the false ideas that are put into motion through the agencies of identities, that shape the contours, the battles over good and evil over the past thousands and I'm sure all of human history. So, since the scientific revolutions that we've enjoyed, especially that burst onto the scene in the Golden Renaissance, a lot of these things, people not only don't get access to the battles, the dynamics of world history that shaped that period, but they don't even get to appreciate really how this is connected to, or was all made possible by something revolutionary that happened in the 8th, 9th century in the Islamic world. And so today, Pascal is going to tackle one aspect of that, and Kevin is going to look at some case study, a very specific, important case study of a particular intellect that shaped and in turn shaped the world, was shaped by and shaped the world, both in his time in the 8th or so century. Kevin, correct me if I'm wrong, but that reverberates all throughout to the present age and into eternity. So thank you guys for doing this. And like usual, when the time comes, put your names, everyone who's listening in the chat box, or put your little digital hand up, and we'll call upon you in queue to ask a question to Pascal or Kevin. So that's all I have to say. Pascal, I think you're going to do part one of the presentation, right? Oh, you're on mute, by the way, and so is Kevin.
Okay, yeah, thanks. I'm just gonna bring my PowerPoint. 1 second. And do this. Oh. So many things here. 1 second.
Yeah, I don't know how to close Windows on my desktop. I'm sorry,
Oh,
Pascal.
I see.
Yeah.
Yeah, that's what I needed to do. Okay, good, good, good. So this is the first slide. Maybe if I can put it as presentation. Okay, there we go. Okay, so hello everyone. Welcome to today's presentation. I just did, oh, Kevin was okay with it. I decided to entitle it Islamic Roots. And I'm going to be discussing some Islamic roots, and Kevin is going to discuss other roots tied to this. So it's a little play on the word roots. So let's jump into this. Okay, some little animations. All right. So Islamic or Islam or Muslims. What do you think about when we hear these words? Well, in the recent days, it's been rough because we've been bombarded by different footage online, on TV, especially since 9/11. The Islamic world has become something strange, something that was part of that was associated with evil. But today we're going to be discussing a different idea of what Islam was as a revolution on a world scale. And so I cannot see my notes here. I had a quote which was went something as they came into our towns and pillaged and looted and destroyed everything in sight. They killed everyone that did not pray to their God and looted our sacred places. Of course, this is a quote from an Arab talking about the Crusades, the Crusaders who invaded the Holy Land. And we can talk also about the Inquisition, which is not exactly part of our best history in the West. And so I would caution people first, if you look at the situation politically today, a lot of people think they know what's going on in the Middle East. Today, we're not going to be going into the politics of it all, but I would say, be very, very cautious. And the idea is going to be to discuss the tendencies, looking at the best, because obviously, in all of history, we have had dark ages and we have had renaissances in all different cultures, and this is part of what we want to address today. The idea of what actually brings about these advances in human knowledge. So the difference between, we could say, a dark age mentality and a city building mentality, or a Renaissance mentality. And so every culture has had some different, I would say, maybe disagreements about how to go about political, religious, and other organizing. So let's go on. In the West, we talk about the Renaissance, looking at the 14th century, 15th century in Italy, and there's this fresco, which is called, I guess people know it if you've been on our presentations before, the School of Athens by Raphael, and you have it right there on the left hand side. This is the whole thing, and on this fresco you have in the middle these two characters that I highlighted in the middle. You have Plato on the left and Aristotle on the right, and basically you see a difference in the way they're moving, the way they're pointing their hands, the books they have in their hands. So you have an epistemological battle going on in this fresco, and all of the different characters, and I don't know all of them. I wish maybe one day Gerald Terrien is going to give us another presentation on that fresco, because he had in the past. So that's maybe a challenge for next time. But there's something in this fresco. We have many scientists, philosophers, discoverers from the past, especially going back to the Greeks. And so obviously the name is the School of Athens. But there's something peculiar on the bottom left hand side. I'm gonna bring attention there. So we have an onlooker, you have Pythagoras, who's uh, writing down or reading, right? Yeah, writing down in a book, and people are looking over to see what he's doing. The one on the top, in green with the turban on his head. I am not 100% sure, but I was searching to figure out who that was, and most people agree that it's Averroes, um, or Ibn Rushd, as he was called. Averroes being the Latinized version of his name. And so I think that's the missing link. That's the idea that we're missing when we think about the Renaissance, as being, we're going back to the Greeks, and they had figured it all out, and we're just taking from them and bringing it, modernizing it, bringing it up to speed to the modern times. And that's what happened. That's how we get the Renaissance in Italy, and subsequently, First Nation states and all that, in our history, modern history. But I think that we need to look more at this question of the link being the Islamic Renaissance, because when Europe was in a dark age, actually, the Islamic world was in a golden age. And so Ibn Rushd has been nicknamed the commentator, because he was a very intelligent man, a polymath, knowing many subjects, studying many subjects. I listed them down on this slide. Many subjects of interest. He wrote many books, more than 100 treatises on these subjects, and he was known as the commentator of Aristotle. So he is one that brought back Aristotle, because before, during the Dark Age, a lot of the Greeks philosophers had been basically disappeared from the map. And so Ibn Rushd was one that brought back Aristotle. I forgot, I wanted to put Al-Kindi was the one who translated Plato. But we're not really going to this battle, this fight right now. This is not the idea of today's presentation. But yeah, so you had different efforts to bring back the knowledge from the Greeks who had been forgotten, and we're going to see why. So I wanted to. Whoops, sorry. I want to start with some different quotes. So the first one being, seek knowledge from the cradle to the grave. Sounds like a good advice to become knowledgeable all your life. The ink of the scholar is holier than the blood of the martyr. Okay, interesting. And seek knowledge even as far as China. So these are all sayings from the Prophet Mohammed, from what we call the hadiths, which are the saying of the Prophet. And so what was Islam for? What was the idea of Islam? Well, obviously it comes, we could say there's a root also to this. And we can go back to the idea of the Abrahamic religion. So going back to Judaism, Christianity, and afterward Islam. One Jewish scholar in Al-Andalus had said that basically that was the idea that the roots were Judaism, then the tree was Christianity, and the leaves were Islam. And if you were going to take down the roots, well, everything was falling apart. So not to do that. And so also to bring concord between the religions. the monotheistic religions of that time. Anyway, so Islam, what for? Well, contrasting to what I said at the beginning, if we look at what has happened in the past decades, all of the wars, all of the fanaticism, it's hard to have a great image of Islam. But if we actually look at the text and what happened at the beginning of Islam, what was the fight to actually get out of the dark age, make sure that the whole world will not get into a dark age when the Roman Empire collapsed. Well, or after the Roman Empire collapsed, these are interesting sayings coming from the Prophet. And especially if we think about the fact that the idea was that when revelation happened, when Mohammed basically started Islam, was given the Quran, well, he didn't know how to read or write. So this is one of the gifts that came with the religion. So that's actually very interesting. That the Quran means recitation, and al-Quran means reading, and so this is kind of a package altogether. Knowledge has to be transmitted. So seek knowledge even as far as China. There's other quotes I wanted to give you. This one being from Ibn Kair in his Farasa. He says, "There's nothing greater in the eye of God than a man who learned a science and who taught it to people." So that was a conscious effort from the beginning to actually bring about the knowledge and clearly the culture, the idea that Islam as a religion, but also the Arabic language as a culture was all in one. And so one came with the other. And the idea was to bring not only the word of God, but also to bring all of the knowledge that mankind had been able to compile, amass since the beginning of time, and to be able to get it into one language also. So we're going to be discussing that. Al-Farabi was also a great thinker in the golden age of Islam, and he was discussing the idea of creating holy cities or divine cities based on that principle of knowledge, of partaking into the knowledge and basically illuminating the world with all of that knowledge. So creating basically academies a bit everywhere across the land. And the term madrasas, I don't know if you ever heard about that. This was the idea of the different schools, library, temples that were all combined in one, and also that from the knowledge of wise of sages, basically, would be transmitted to the masses. So not just to few people, but actually would become a public education system. So that also was part of the advancement that happened during the golden age of Islam. This is the city of Baghdad. I wanted to go a bit backwards. Instead of going from the beginning of Islam to the end, I want to go a bit from, well, it never ended, but a very important historical marker was the fall of Baghdad. But what was Baghdad? Well, Baghdad was actually an older city that was reorganized when Islam made it its religion, when the Abbasid Caliphate made it its capital. So in Baghdad, you had what were called what was called the House of Wisdom, founded in 832. This was the center, basically, of an effort to encompass all of human knowledge and bring it and translate in Arabic. So the translation movement was a very important uh, figure of the city. You had translators who were, of course, Arab, Jews, Christian, Indians. They translated from Greek, Hebrew, Pahlavi, which is kind of the Persian language, Syriac or Aramean, and Sanskrit. Other language, I didn't list them all, into Arabic. So all of the knowledge from these different cultures, were actually translated in the House of Wisdom in Baghdad, and other houses of wisdom were deployed everywhere in the Caliphate when as Islam was growing and taking possession of different lands. But that's it. If we're going backwards, 1258 is a very dark year. It's a bit like on the western side, for those who remember, well, those who have an idea of what was the Library of Alexandria. That's basically what happened in 1252 in Baghdad. The Mongols, the grandson of Genghis Khan, took over the city and destroyed it. Basically, destroyed the House of Wisdom, burnt everything, and so we lost. What had happened at the in the House of Wisdom? Hard to say really how much we lost, but certainly a lot. Hope in the hope also, well, thinking of all the translations that were spread all over the place. Hopefully, a lot of that is what was developed in the House of Wisdom. It's hard to tell, because everything was destroyed at the time. So this is really, we could say, the downfall when the Islamic culture basically went into a dark age after the Golden Age. That's the Mongols took over. The Umayyad Caliphate, I'm just showing you the map just to give you an idea of how it looked. So after that's, we're going back now. We're at the beginning of Islam. So 622 is the year of Hijra. So the beginning, basically, of the Muslim era. And so 661 to 750 is the Umayyad Caliphate, and they basically take over the whole southern Mediterranean region and up until the western border of India. So it's a very fast spread that happens at the time, and you can think the Roman Empire had collapsed, centuries before, but the land was organized politically in many regions of northern Africa, Spain, and all that. So actually, it was not exactly just like I said in the beginning. It was not looting. It was not necessarily that. It was not barbarous destruction. It was actually filling the gap, filling the void of what was happening at that time, and actually bring a new order to have basically fallen in shambles following the collapse of the Roman Empire. So that's what they were filling the gap for. This is to give you another representation of how the different steps, how it evolved. So you see the from Arabia here on the right hand side, and the development into Persia, Egypt, Maghreb, and then Al-Andalus, which we call Spain today. So all of these regions were conquered at the time by the different caliphates. The first one being the Umayyad, which I just showed you. But not all rosy and nice. So there were different internal fights, and I'm not going to go into the theological fight that happened between the Sunnis and the Shiite. That would be for a whole presentation on its own. But suffice it to say, there were internal fights into the Islamic Empire at the time, and the Abbasid was a different dynasty that came up and took over, and so the territory was cut in different pieces. The caliphate, there was a caliphate that still existed in Al-Andalus, Spain, in the Maghreb, but this is just a map of the Abbasid Caliphate, which reigned from 750 to 1250, and that's during that period that we had the development of the House of Wisdom in Baghdad. Harun al-Rashid was one of the caliphs during that time of the Abbasid Empire, or Abbasid Caliphate, and he had developed embassies, ambassadors going around and making treaties, organizing, and you on that painting, it's a representation of Harun al-Rashid on the left, looking at emissaries that come from the Carolingian Empire, so Charlemagne, the Franks, basically, who were bringing gifts to one another. And so Harun al-Rashid also sent an elephant, a white elephant that came from India, to Charlemagne as a gift. And Charlemagne sent horses and dogs and different other presents to Harun al-Rashid. There was actually an agreement that Charlemagne was the depositary of the city of Jerusalem, and so that the access to the Holy Land was secured through these embassies, these different groups that came back and forth from the Abbasid capital in Baghdad to the Carolingian Empire at the time, which was based in Aix-la-Chapelle. So there was a fight for ecumenical entente, basically bridging the differences between the different religions at the time, and so different efforts were done on both sides. Obviously, the situation was not as good on Charlemagne's side, but on Harun al-Rashid, there was a development at the time situation. I'm going to try to go a bit faster. I want Kevin to get you all alive and well. So just going to go a bit more speedy on this part. Different adaptations and contributions. So we tend to forget all of the development, the science that had been lost because the destruction of the Roman Empire had brought down the cultural exchanges between different parts of the land, and a lot of authors were disappeared. Basically, the printing did not exist at the time, so a lot of that was kept and not shared for a long period of time, except from the translation movement. So preservation, and also what helps is the invention of paper. So the Chinese had invented paper, and the Muslim actually perfected it, so you could actually write on both sides. And the translation movement was a big factor into this. The effort by Harun al-Rashid and his son al-Mamun, the two caliphs, were pretty much the ones that drove that made it an imperative to translate everything they could find they would translate it. All the knowledge from all the different cultures previous was incorporated by the translation in Arabic. You have the development of astronomy. Observatories were built in Baghdad, in Cordoba, everywhere, basically, all across the Muslim, the Islamic caliphates, and that helped for knowing where you were on the planet. Uh, it is known that Copernicus was using the work of different Arabic scholars, and I named a few of them, like al-Shatir, al-Tulsi, and al-Urdi, um, for prayers, because that's a religious commandment. Yeah, if you're Muslim, you have to pray 5 times a day, and it's not based on the solar calendar. It's based on the moon calendar, as for the Chinese. So they have the same kind of problem, and they had to develop astronomy, great knowledge of it to understand when to pray, because it changes over time. It's not always the same constant time. So and also when navigating and mapping places, you hope that the people knew what we're doing. Otherwise, you better pray. So architecture, there was development of architecture. I showed you some pictures at the beginning. Art, music, a lot of music and poetry, especially the language. Development of the language brought forth a very big emphasis on poetry, and that translated into also how we write poetry, or actually how the Italian canzone was developed afterward, Dante, in Dante's time. Obviously, I'm not going to go and give you examples of all of them, but I touched on a couple ones. Diplomacy at the end. So there was an effort to spread, to acquire knowledge, but also to spread, to have good friendship with different nations, or at least have contact with them. In medicine, different names come back, like Ibn Sina, Avicenna, that's the name we call him in the West. Ibn Nafiz, al-Razi, hygiene, hospital system, separating pathologies, all of that. Obviously, they didn't necessarily reinvent the wheel, as we say, but there was a lot of adaptation that came from earlier knowledge, earlier technologies, and that were improved upon, discoveries that were made by the different doctors. And Ibn Sina, Avicenna, his book, The Canon, was actually has been used since 1052, I believe, or 1020 was written, and it was really like the name says it was the canon of medicine. It was really like the knowledge we had of medicine was very well compiled for the time, until I think the 18th or 19th century, basically. And also there was an effort to take care of people that had mental illness. So psychological wards were also developed. So instead of ostracizing people that had mental issues, they would try to actually protect them, or try to understand what was going on. Infrastructure, canals, over and underground, were developed. So that's also something that was improved upon. Dams, windmills, agriculture. Obviously, if you live in the desert, how are you going to grow food? Well, you need to develop a very good infrastructure to do that. And so that was part of the effort of city building. And I'm trying, that's really the idea, city building, instead of this idea of, barbarian fanaticism. There's the two factions that collide all the time, and that's really what we have to keep in mind, is what had to be the impulse, what had to be the idea of man that was carried through that made possible these developments. All of the salvaging of the science and the culture that previously was developed by different cultures, the Greeks, the Indians, and basically that came forward after that. I'm gonna go a bit faster. I'm gonna skip that. Of course, you know about the Arab numbers, 1, 2, 3, 5, and so on. That's I put it in quotes because it's not exactly Arab. It really comes from Indians, but they made it popular. Let's put it like that. So it became known as the Arab numbers. Representation of the House of Wisdom, development of astronomical tools. The astrolabe, for example, was developed by the Arabs. At the House of Wisdom, chemistry or alchemy also was a topic at the time. So on the right hand side, different mixtures, maybe cures or poison, depending on how you use them. So that's what's depicted there. Different markers. I wanted to give you an idea because it's not so obvious for us in the West to try to put things together. When things happen, oh, I think there's some missing. Yeah. Oh, sorry, it didn't end the last one. Okay. So on the Western side, I think people have an idea, except I added some stuff. So if we look at what starts at the bottom, the Eastern and the Western Roman Empire become splitted. Oh, well, yeah, the last part, forget about the last part. But from 286 to 395, the Roman Empire was splitted to try to organize it differently, and eventually it really became an official split in 395. And after that, not long after that, the barbarians, the Visigoth, basically sacked Rome with their king Alaric in 410. The real collapse, well, what we put in as the year of the collapse, the official collapse of the Western Roman Empire is 476. And we go back on we go on the other side. So the birth of Islam is around 610, or the year of Isra, I think, is 622. Because at that point, basically, like for the Christian who says, the year 0 is the birth of Christ. Well, for the Muslim, the same thing. The idea is that there's a year 0, and it's when Islam started. So it's around that time. 711, the Islamic conquest of Spain and India. And so I wanted to contrast. So you have a fight to reconquer, to get it back. In 722 starts the Reconquista, right? And the last date I gave you is the end. So the start is in 722, and the end is in 1492. It ends the Reconquista of Spain, basically, which was Al-Andalus under the Caliphate. 780 to 850, there's a character here, al-Khwarizmi, which Kevin is going to talk to us about. Not say too much. I gave you some dates for the reign of the different caliphs. So Harun al-Rashid and his son al-Mamun, who started the House of Wisdom. And you have the different authors I gave you. I wanted to give you the dates for them also. And the siege of Baghdad, which was the sack of Baghdad, the destruction by the Mongols, and basically the downfall ever after the end of the golden age of Islam. Another date interesting that I think Kevin is going to talk about, or just to introduce the subject, is here, 1145. Yeah, Robert, who translates al-Khwarizmi, his book on algebra in Latin, and he was based in Spain. So that's where he learned. He learned about al-Khwarizmi and the development of the science that was going on in Al-Andalus. I think I'm gonna end there because I said I took a lot of time already, and I want Kevin to give us his knowledge about al-Khwarizmi. So this is gonna be it for me. Thank you. And I'm gonna stop my share. It's all yours, Kevin.
All right. Well, thank you, Pascal, for this historical context. I'm going to share my screen now for the second part of the presentation. See here right now. Oops. All right. So, Islamic Roots and al-Khwarizmi's Algebra. So basically what, to go off of what Pascal said, is to think about the Islamic Golden Age as the bridge that was necessary for the Renaissance to take place, in Europe afterwards. And I think the last that Pascal presented shows that pretty well. And we're gonna keep in mind the Reconquista of Spain, because this is basically the way by which al-Khwarizmi's work was transmitted to us, well, during almost at the end of the Reconquista with Robert of Chester. I'm going to touch a little on. But before going there, I want to, as far as introduction goes, to talk about algebra in today's high school curriculum, because algebra is going to be the focus of today's of my the second presentation. And so I just want to go through very quickly all of the algebraic manipulations that are taught in today's schools, and most of you here have learned in the past probably most or all of the methods to solve what are called first and second degree equations. So just so that we're all on the same page, the first degree equation would be an equation in which you have an x, in which the x has an exponent of 1. So for instance, x equals 0 is a first degree equation. And the second degree equation would be this one here, x equals 0. It's a second degree equation because you have an exponent of 2. Okay, so now that's so we can go on. So what do kids learn in school today? So they learn to manipulate those symbols, like the factoring out the greatest common factor method. So you have your x, then you can remove the x, and you have x times x plus 5 equals 0. And so therefore, x either equals 0 or minus 5. Not too bad. Then a little farther along the course or the curriculum, they would learn something like the factoring by grouping, where you have something like this: x squared plus 2x plus 5x plus 10 equals 0. And remember that we go here in algebra is always right to find the value of x. And so in this method, well, people will learn to notice that we have an x that is common to both the first and second term. So you can do a factoring of the greatest common factor on those two terms. You have a 5 that is common on the third and fourth terms. And then on the first term of the second line and the second term of the second line, you have x2 that is common. So you can put that and factor it out, which gives you x plus 2, x plus 5. And so you have the solution to this type of equation: x is either minus 2 or minus 5. Afterwards, you have the products of medicine, which personally I like the least because it's basically a trial and error method that is taught in school. Here, I've used the same, basically the same polynomial, which gives you the same result, -2, -5. But here, what you do is you ask yourself what number, when you add them together, gives you 7, and when you multiply by themselves, that will be 2 and 5, and so this is your solution. Then we get to the 3 other methods are taught later in the curriculum. Actually, the latest in the curriculum, all secondary methods. Put a name there. Okay, so you'll see first on the right hand side, you see like the algebraic manipulations that are in school. It's very symbolic, right? And that's one of the reasons why I would guess that most of the students today, it goes over their head what they're doing. They learn like by heart what they have to do, but they don't actually quite understand what's happening there, right? And actually look at the name of those methods. So the perfect square trinomial. Then you have the difference of squares method. And this one is quite funny because you have x squared minus 25, which is x squared minus 5 squared, sure. And then x plus 5, x minus 5. Gives you the symbolic right in mathematics to do that. Like how to make sense of that. And then you have the completion of the square method, which is quite hardcore. We're gonna, at the end of this talk, hopefully I'm gonna give you enough context and the right mindset to maybe approach it by yourself in an easier way, let's say it, or intuitive way. But yeah, the perfect square, the difference of squares, and the completion of the square. So those who know a little bit about mathematics know that exponent 2 is often said squared. Sure, but when people talk about square, they think about geometric square, right? They think about the figure. They don't think about necessarily multiplying something by itself. And finally, you have the quadratic formula. So defined as minus b plus minus square root of b squared minus 4ac divided to a, which student just learned by heart yet again, because this is the no-brainer formula that works all the times. Sometimes you have no solution, sometimes you have one solution, sometimes you have 2. Why does that happen? We don't really know. But, it works, so we're going to apply it. So what I want to focus today is on, the geometric quality of numbers. Because as I pointed out, there's like the perfect square, the completion of the square. Where does that come from? So to get ourselves the right mindset, I selected a little passage from the Theaetetus of Plato. I thought it was quite fitting since the Theaetetus was read in some recent RTF lectures. And so if people would be willing, I would like to have 2 people read this passage that I've selected. It's a simple slide, so it won't be too much long. I would just need one Socrates and one Theaetetus to read this passage, and then I'll continue on myself. So do you have some people, some volunteers?
I volunteered, Jerry.
I was going to do the same.
Thank you so much.
I'll volunteer myself too.
So, Jerry, do you want to do Socrates or Theaetetus?
Doesn't matter. Whichever you prefer.
Okay, you can
Okay,
start.
well, I would like for you to do Socrates. He's the old wiser guy.
Thank you. Okay, I'll be Socrates. You hear, Theaetetus, what Theodore says, and I suppose you will not care to disobey him, as indeed it is not permitted for a younger man to do when a man learned in such matter gives his commands. So let us have good, clear answer without stint. What does science seem to you to be?
Well, I suppose I must reply, Socrates, since you and the rest desire me. Or, of course, if I do make some mistake, you will set me right.
Oh, certainly. That is, if we are able.
Well, then, I think that what one can learn from Theodore may be called sciences, geometry, and those you just named, and again, shoemaking and the trades of the other craftsmen, and all and each of them are nothing else than knowledge.
Like a generous and free-handed man, my friend, when asked for one, you offer many, and various for simple.
What do you mean by that, Socrates?
It has no meaning, perhaps, but what I think I intended to say, I will explain. When you speak of a cobbler's art, do you mean by it anything else than the science of the manufacture of shoes?
Nothing else?
Well, when you speak of carpentry, is it of anything but the science of manufacturing wooden implements?
My reply is the same in this case too.
Then in both you confine your answer to that, of which each art is science.
Yes.
But, my Theaetetus, the question asked was not this, of what things knowledge is the science, nor how many sciences there are. For it was not with any wish to count them that we asked, but to get a clear knowledge about science, what it is in the abstract. Or is there nothing at all in what I say?
Indeed, you say very rightly.
Now then, consider well what I'm going further to remark. Supposing a person should ask us about some commonplace and obvious thing, for instance, what is clay? Should we not appear ridiculous if we answered him, clay is the clay of the potters, and also of the porcelain makers, and of the brick makers likewise?
Perhaps we should.
In the first place, I presume, in supposing that the questioner would understand what clay was from, our answer, clay is clay, adding either such as the image makers use or any other artist, say, you please. Do you believe that a man understands the name of a thing if he does not know what the thing itself is?
No means.
Then one who does not know what science means cannot understand either the science of shoes.
He can.
And again, whoever is ignorant what science is does not comprehend the knowledge of leather or any other trade.
That is so.
Then the answer is absurd when a man is asked what is knowledge, if he gives in reply the name of some trade. For his answer is confined to the knowledge of some particular subject, but he was not asked that.
So it seems.
Thus then, when he might, I suppose, have answered in a common way and in brief. He goes a roundabout way that has no end to it. For instance, in the question about clay, it was obvious, surely, and simple to reply that earth mixed up with any fluid would be clay. And you need not concern yourself as to whose clay it is.
Yes, it appears easy enough now, Socrates, when you put it thus. But your question seems like one which lately presented itself to us when we were talking. I and your namesake here, Socrates.
What was that now, Theaetetus?
Theodore here was writing down some facts about the powers of numbers and showing us that a rectangle composed of 3-foot and 5-foot line is not geometrically commensurable by the 1-foot line. And so he went on taking examples one by one up to the 7-foot line. And at that, he stopped. The idea then occurred to us, as these powers seemed indefinitely numerous, we should try to comprehend them under some one general term, by which we might describe all those of this kind.
Did you then find such a term?
I think we did, but consider it also yourself.
Tell me then.
We divided all number into two kinds. That which could be resolved into an equal number of factors, we compared to a figure square in form, and called it both quadrangular and equal-sided.
And very appropriately, too.
Well, the intervening numbers, such as 3 and 5, all such as cannot be resolved into equal factors, but can only become either more taken fewer times or less taken more times, and so, do as you will, must ever be enclosed by one side that is greater than another side. This kind of numbers, we compared to the oblong form and called it long number.
Very good indeed. But what next?
All the lines which make up an equilateral rectangular superficial area, we distinguished as regular, and all that include as parallelogram as powers, on the ground that, in linear figure, they were not commensurable with those other lines, but only with the superficial squares they were equivalent to, and similarly with cube numbers.
None could possibly have done better, my dear boys, so that Theodore, as it seems to me, will not be held liable to the penalties of perjury.
All right. Thank you, Pascal. Thank you, Jerry. So here we see that Theodotus, trying to answer what science is, as the idea to make a parallel with a discussion with his teacher Theodore about classifying numbers between square numbers and rectangular numbers. Seems to him that some numbers had some geometric quality that other numbers didn't have. So let's look at them. We have 1, 4, 9, 16, 25. All those numbers can be called square because we can form a square with them. In all those numbers, you have the others, which we would call, well, which Theodotus calls long numbers or rectangular numbers. He also mentions cube numbers. Well, we can find them in those lists in this here. 1, 8, 27 are also special numbers. 8 and 27, they're not square numbers, but they are numbers. And here is how we would represent them. You have 1, 8, and 27. Let's go a little bit farther. fun. Here you have Pascal's triangle, which is another Pascal. So most of you have probably seen this in your math courses. I'm not going to go into the details of it too much. Just know that how you can construct this triangle is that first you have, well, the first line and the first, or either the first column and the first line, which are all ones. And all the other numbers are, you get them by adding the one number that is on this line and in the previous column. So if you have 4 here, it's 3 plus 1, you get 4. So why am I bringing this up? Well, like I said, you have those 1 here. And then in the second line slash column, you have 1, 2, 3, 4, 5, 6, 7. But what's interesting is when you get to the third line, or the third column, you get triangular numbers. Because with all those numbers, 1, 3, 6, 10, 15, 21, sorry, you can form triangles with them. Another interesting thing is that when you go on the fourth line, well, you get Perman numbers. So 1, 4, 10, 20, 35. And now just to prick at your brain a little, if the third line is triangle numbers, so in 2 dimensions, and the fourth line is Perman numbers, meaning in 3rd dimensions, are those the equivalent of triangular numbers in 4 dimensions? Can we go there? Is this mathematically or realistically or physically legit? I'll leave it for you to answer or think about. So now that we've put numbers in a geometrical context, we can talk about Abu Abdullah Mohammed ibn Musa al-Khwarizmi. I hope I haven't massacred his name too much. So here's the picture. This is a stamp that was commissioned, I think, in the late 19th century. No, in the early 1860. Late in the 20th century, sorry, by the Soviet Union. It's pretty much the only image we have from him, because actually we don't know much about al-Khwarizmi. We know very little, in fact. So like Pascal said, he was born around 780, born in Khwarizm, but this is debatable. He maybe was born in the region of Baghdad, but his family was born in Khwarizm, but it's not much important. Khwarizm is in modern day Uzbekistan, so to the east of the Caspian Sea. And he died about in around 850. So as you can surmise from his name, al-Khwarizmi means from Khwarizm. So yeah, at a young age or before his birth, we don't know, his family were settled around Baghdad. He was appointed to work in the House of Wisdom, which Pascal talked about a little, and which was established under Mamun. And at one point, I'm not sure if he was one of the first or the first, but at one point he was the head of the library there, and basically the whole, House of Wisdom. He was a true polymath because he worked in many fields, including geography, cartography, astronomy, history, and mathematics, which he is most known for. He wrote many books, but for some of the reasons that Pascal talked about, and for others, many of those books are now lost to us, either because they were destroyed or, any other reason. He's best known for transmitting techniques, methods, and concepts coming from India and the Far East to the West. while adding his own innovations and improvements to them. So Pascal touched on that a little, meaning that the Islamic Golden Age was really acting again as a bridge between the past and the far region of the earth and the future, while adding their own improvements in many fields. And al-Khwarizmi played a big role in this. He is credited with being the one to transmit the Indo-Arabic numerals. So the Arab numerals are not like the right name, really. It's really the Indo-Arabic because it's a mixture of both. He also credited with transmitting the zero to us, which also came from India. The decimal point also, and fractions. So fractions were used before, meaning that, let's say, 1/2 was written 1 and 2 on top of each other. But al-Khwarizmi and the Muslims added the famous line in between the two numbers. So fractions that they really come from there. And lastly, something that is very pertinent to our day here is that the word algorithm, which you will recognize in algorithms in social media or computers or in everyday life, really comes from the Latin word algoritmi or algoritmus, which is a transliteration of al-Khwarizmi. So just to give you a sense of how the guy was important, the word algorithm, which today means a set of instructions to accomplish a goal, basically, comes from this guy. So it gives you an idea of how big of a role he played in our culture. Now we come to the book that we're gonna do the rest of the talk on, which is the compendious book on calculation by completing and balancing. So here you have the title in Arabic. You'll notice here algebra, which, well, as you can guess, the root of the word algebra. This is where the name comes. So congratulations to al-Khwarizmi. He both is the originator of the word algorithm and algebra, which are both big concepts in today's sciences. Algebra means restoration or completion. Al-Muqabala means opposition and balancing. We could talk about this more in detail. When I was in college, this is how we introduced al-Khwarizmi through those two concepts, because it's pretty much attached to algebra as it is taught today, meaning as symbols. But I don't want to focus on that today. I'm going to focus more on the geometry of the algebra. As Pascal said, Khalifa Mamoun, well, he didn't quite say that in particular, but Khalifa Mamoun commissioned al-Khwarizmi to write that book because he wanted a book that was accessible and practical to the common man, and that would help them explain and understand how to solve common mathematics problem and mostly economic problems. The book was translated from Arabic to Latin by Robert F. Chester, others, around 1183. And here we really need to understand the importance of the Conquista of the Spaniards, because this is how we actually had access to that book. Because when al-Khwarizmi wrote the book, it propagated throughout the whole Abbasid Empire or Caliphate. It reached Spain, and then when the Reconquista was in the process of going on, is when the Europeans had access to those books, and then Robert of Chester translated it to Latin. And this is pretty much the book that I'm gonna get the text of from. Sorry. And finally, before we get into the meat and potatoes, the content of the book. So chapter 1 to 6 is explanations of first and second degree equations. So basically what it does is that he separates all cases or all 6 different natures of equations and explains how to solve each and every one of them. What we're going to do today is look at how he explains chapter 1 to 4. So the first 4 cases. 5 and 6 we're gonna skip, especially 6 we're gonna skip, but the 5 I'm gonna use it to bring back home in today's algebra and see how we can re-explain this particular case using today's thinking about algebra. The reason why we are going to skip it also in 5 and 6 is because it's quite the demonstrations are quite complicated, and I think it would go out of today's talk. That's not what we want to do here. I'm going to also mix chapter 7 and 12 because they are the demonstrations basically of why his explanations work. So we're going to read chapter 1 to 4 and use the explanation of 7 to 10 to show why it works. Chapter 13 is the multiplication and positive and negative numbers. So this is something to keep in mind. During the presentation, try and look for negative numbers in what I'm going to show you. And we're going to get back to that. Chapter 14 is the multiplication and division of roots and fractions. So it shows you how to multiply, say, the root of 3 with the root of 4, let's say. Chapter 16 is 6 additional problems in relation to chapter 1 to 6. Chapter 16 is 16 other problems. And chapter 17 are problems relating to working transactions. So you can think of the compendious book on calculation by completion and balancing as really a textbook for students of the common folk, let's say. So let's start. I'm going to read the introduction and then chapter 1 to 4 and show you some of his thinking, how he thought about algebra. So the book of Algebra and Al-Muqabala concerning arithmetical and geometrical problems. In the name of God, tender and compassionate, begins the book of restoration and opposition of numbers put forth by Mohammed al-Khwarizmi, the son of Moses. Mohammed said, "Praise God, the Creator, who has bestowed upon man the power to discover the significance of numbers. Indeed, reflect that all things which men need require computation. I discovered that all things involve number, and I discovered number is nothing other than that which is composed of units. Unity, therefore, is implied in every number." By the way, I forgot to mention, but I sent the PDF of the book to Matt by email. So normally it should be available in the description of the video when it's on YouTube, hopefully. Moreover, I discovered all numbers could be so arranged that they proceed from unity up to 10. The number 10 is treated in the same manner as the unit, and for this reason doubled and tripled, just as in the case of unity. Out of its duplication arise 20, and from its triplication 30. And so multiplying the number 10, you arrive at 100. Again, the number 100 is doubled and tripled, like the number 10. So by doubling and tripling, etc., the number 100 grows to 1000. In this way, multiplying the number 1000 according to the denominations of numbers, you come even to the investigation of number to infinity. So, quite cool that, in fact, as an introduction, he's just setting the stage to say that, numbers are composed of unity. And here's basically how he thinks about and how we think about today as numbers. So we have the number 1 through 10, 10 being 1 unit of 10 smaller units. And then when you have 10 packets of 10, you have 100s. And when you have 10 packets of tens of packets of tens, then you have 1000s, and etc., etc., etc. Furthermore, I discovered that numbers of restoration and opposition are composed of these 3 kinds, namely roots, squares, and numbers. However, number alone is connected neither with roots nor with squares by any ratio. Of these, then, the root is anything composed of units which can be multiplied by itself, or any number greater than unity multiplied by itself, or that is found to be diminished of unity when multiplied by itself. The square is that which results from the multiplication of a root by itself. So what he says here is that when you look at second degrees equation, so the one that I showed at the beginning of this presentation, you can look at all the numbers there, or all the terms in the equation, 3 ways. So you have the numbers. Numbers are composed of units. I will represent them in green. You have the roots, and roots are composed of numbers. Here it's very important to understand that roots are side of a square. So here is the same length as one of the sides of the square. It's not longer or smaller. It's the same thing, or the same length. To represent the root as x. So al-Khwarizmi really thinks about the root as x. And then we have the square, and squares are composed of you obtain squares by multiplying a root by itself. So 2 multiplied by 2 gives you 4. 4 is the square, and 2 is the root of 4. Today we will represent that as x squared. So with this, we have this passage here, and then he's gonna go into the first 3 chapters. So of these 3 forms, then 2 may be equal to each other, as for example, squares equal to roots, squares equal to numbers, and roots equal to numbers. So chapter 1, considering squares equal to roots. So the following is an example of squares equal to roots. A square is 5 roots. The root of the square then is 5, and 25 forms its square root, which, of course, equals of its roots. Okay, so you gotta understand that when he gives the explanation, it's always in written form. So, well, in the first 6 chapters, there's no drawings or anything, no algebra as we think of it today, no symbolism, just plain explained in words. But what does he mean exactly? So you have your square, and it's equal to its roots. You have 1 to 5, and they all have a length of x. Today we would write as x squared equals 5x. Well, when you put all the 5 roots together, you know that you have 5 of them, and you know that it's equal to the square. So necessarily, the root of length 5 and 25 is the square. So they will x equals 5. Another example. The third part of the square equals 4 roots. Then the root of the square is 12, and 144 designates its square. So the third part of a square here, so we have less than 1 square. It's equal to 4 of the roots of the square. Today we will write it down as squared over 3 equals 4x. Well, it goes without saying that if you have the third part of a square, we want to work with 1 square. So what we're going to do is multiply the square by 3 to have a complete square. But since it's an equation, and an equation requires that everything is balanced, we have to multiply the number of roots by 3 also. So then we end up with 12, sorry. And since we have 12 roots, well, the one root is of length 12, and 104 is the square. So x equals 12. Then he ends chapter 1 with this. And similarly, 5 squares equal 10 roots. Therefore, 1 square equals 2 roots, and the root of the square is 2. 4 represent the square. So we started with 1 square, then less than a square. Now we have more than 1 square. We have 5 of them now. And it says that it's equal to 10 roots. Today we will write it down as 5 squared equals 10x. So what he says is, well, take fifth of all the squares and a fifth of all the roots. You'll get that 1 square is equal to 2 roots, and therefore 2 is roots. Therefore 4 is the square. So in the same manner, that which involves more than 1 square or is less than 1 is reduced to 1 square. Likewise, you perform the same operation on the roots which accompany the squares. So here's basically what he means. Whether you have less than 1 square or more than 1 square, back to 1 square, and you're going to solve your problem. This is step 1 of his algorithm. Now we get to chapter 2, concerning squares equal to numbers. So now I'm gonna, from now on, I'm gonna look only at cases where he explains how to solve a case where it's 1 square, because you know now that if you have more than 1 square or less than 1 square, you just get back to 1 square, and then you do what he's explaining here, what you have to do. So squares equal to numbers illustrated in the following manner. A square is equal to 9. Then 9 measures the square of which 3 represent 1 root. So he's saying, well, a square is equal to 9 units, which we will write down as x squared equals 9. Therefore, x equals 3, or 1 root of the square is 3. So again, if you have 2 squares, then you would have 8 units, but you divide both by 2, you would get back to this part here, and you solve the problem as he explains here. If there are many or few squares, they will have to be reduced in the same manner to the form of the 1 square. That is to say, if there are 2 or 3 or 4 squares, or even more, the equation formed by them with their roots is to be reduced to the form of 1 square with its roots. Further, if there be less than 1 square, that is, if a third or fourth or fifth of a square or root is proposed, this is treated in the same manner. So by now you understand that go back to one. This is first step of the algorithm. Chapter 3, concerning roots equal to numbers. The following is an example of roots equal to numbers. A root is equal to 3. Therefore, 9 is a square of this root. So this is pretty simple. You have one root, and it's equal to 3 units. So basically saying x equals 3. But, okay, that means that 1 square is 9. All right. And then again, if you have more than one root in this case, you get back to one root. And if you have less than one root, then you go up to one root. Therefore, roots and squares are, and pure numbers are, as we have shown, distinguished from one another. Whence also from these three kinds, which we have just explained, three distinct types of equations are formed involving three elements, as a square and roots equal to numbers, a square and numbers equal to roots, and roots and numbers equal to a square. So the first three cases, or the first three chapters, are pretty simple to understand, pretty easy. Now we're going to look at chapter 4, which is a square and roots equal to numbers. After that, I'm going to use a square and numbers equal to roots to present a more modern way to use al-Khwarizmi's method, I would say geometric method, and the roots and numbers equal to square we're going to see, because with that point, we're going to spend enough time on that. So chapter 4, concerning square equal to numbers. So this is where it gets very interesting. So the following is an example of squares and roots equal to numbers. A square and 10 roots are equal to 39 units. The question, therefore, in this type of equation is as follows. What is the square which, combined with 10 of its roots, will give a sum total of 39? The manner of solving this type of equation is to take 1/2 of the roots just mentioned. Now, the roots in the problem before us are 10. Therefore, take 5, which multiplied by itself gives 25. An amount which you add to 39 gives 64. Having taken then the square root of this, which is 8, subtract from it the half of the roots, 5, leaving 3. The number 3, therefore, represents one root of this square, which itself, of course, is 9. 9, therefore, gives that square. So, first of all, you have the equation here, as we write today, x squared plus 10x equals 39. And by his method, right, he's just saying, here is just telling you what to do. He's not explaining anything. This he will do in the later chapters, but I'm going to show you what he's actually doing in the next slide. But we understand that 3 is really the root, because 3 squared is 9. And when you add that to 9 times 3, which is 30, you really have 39. So, I mean, this methods work here. And we're going to see why it always works. Of course, with a particular example, but you can try it with pretty much every other cases. It's going to work. So here on the left side, I've condensed his method into an algorithm, right? So first, you start by simplifying to a single square, like we've learned from chapter 1, 2, 3. This is the case because the equation is x squared plus 10x equals 39. So this is how we would represent, right? You have one square, you have roots, and here you have 39 units. Then he says, take 1/2 of the roots. Okay, that's pretty specific. Why do that? Well, this is why. Because you're going to split the roots into 2 groups, where you're going to stick one of the groups on the right side, one of the groups on the bottom side. Now, a little side note here. I'm using the second demonstration that he's using in the book. He's actually started the chapters on demonstration with another technique, which is basically to separate the rectangles or the roots in 4 groups and to stick them on all 4 sides of the square. But then you figure out that it's actually better to just put them on 2 sides, which he shows. And so I'm going with this method because I think it's simple. So you take 1 roof of the roots and you stick them to the square here, and it's still equal to 39. Then he said, you multiply that number meaning the 5, by itself, you add it to the units. Okay, so why multiply the number 5 by itself? Well, I don't know if you see here, but on the bottom right corner, if we would fill that, we would complete the square. And what we would need to complete that square is 25 units, because we know that this is 5 of length, because we have 5 roots on this side, and we have 5 roots on that side, which gives us 25 here. So that's why he says to do that. So this is what happens when you add the 25 units. So when you add the 25 units, you have 64 units in total. Great. Then take the root of the total numbers of units. Well, we know that we have 64 units on the right side. So the root of that square, 1, 2, 3, 4, 5, 6, 7, 8. And we're going to do this on the left side, meaning that we're going to ask ourselves, what is the root of this square, or what is the length of that of one side of the square? Well, it's we don't know the root of the square plus 5 units. So that's why I've written here x plus 5 squared. Right? And it's equal to square. And then he says, remove the 1/2 of the root from that, meaning the root of the square, and you get the root of the square. So what he says is that you have your 5 here, remove it from the 8, and you're going to get the root of the blue square. So what he's saying is basically remove all the excess here and do the same thing on the right side. So we're left with this. And therefore, x is equal to 3, or the root of the square is 3, and the square is 9. So this is basically al-Khwarizmi's method. Now, as I said in chapter 5 and 6, it gets a little bit more complicated. And the reason why it gets a little bit more complicated is about this right now. I asked you earlier to take notice of negative numbers in al-Khwarizmi's method. But he didn't use negative numbers, actually. That's the thing. He only uses positive quantities. So here is a table that resumes all the 6 chapters. Okay, we looked at 1 through 4, x squared plus bx equals c being the last one. So we would write them down as basically the same way we did in the first slides that I showed you, the way we teach factoring in today's school, we would have squared minus bx, squared minus c, bx minus c, and so on and so forth. And so when al-Khwarizmi demonstrates why his methods work and do work, has to go through quite complicated geometrical demonstration, which is kind of accessible, but it's quite lengthy. So we're not going to go through it. So the question remains, why only use positive quantities? Because as I presented earlier, later in the book, he shows you how to multiply positive and negative numbers. So it's not like they don't exist. It seems that they just don't want to go there. So I'm going to end the presentation by presenting to you an adaptation of one of the examples that he shows in chapter 5. And this might go over the head of people here. That's okay, because if you haven't studied mathematics, maybe you don't know what to look for, or you don't know quite what you will see. But if you pay attention, you're going to see, I'm going to, wink, wink, nod, nod, make suggestion as to what's going on, or what's in what's happening here. So the example that he gives is that a square and 21 units equal 10 roots. So this is the equation that we would get literally from what he writes. This is how he solves it. What I'm going to show you today is a squared minus 10x plus 21 equals 0. Basically, what we would say today, to transfer the 10x on the other side of the equation. I'm going to look at what's going on here. So we start with square of x by x. So the root of the square is x, and x squared is square. Now, if we look at the equation, it says minus 10x. It's as if we're saying, well, remove from that square the root. So what we do, and it's going to reflect a little bit on how al-Khwarizmi shows the demonstration. There's some similarities between both methods. So we start by removing 5 roots, 1, 2, 3, 4, 5. So this side here measures the root minus 5. Then we do the same thing here. We remove another 5 roots. So all the 10 roots are removed. The thing now is that, well, here is like a piece of paper of which I've removed a part. And here on the bottom right corner, it's as if I'm removing something that's already not there. Right? So single hashed part here is actually 0 with nothing, right? But I can't remove something from nothing. Kind of doesn't really make sense, right? So you have minus 25 here. This is my wink, wink, nod, nod. What does that represent, the minus 25? Not sure if it's legit, but we're still going to work with it. Now, I've rewritten also the x minus 5 because we've removed 5 roots there and 5 roots like this. We are left with the square of x minus 5 by x minus 5. Then we add the 21 units, right? So you see in green the 21 units. So the 21 units, it's plus 21, right? So it's squares with that have a positive. We're okay with this, okay? It's the squares with negative values that are a little bit funky. But as you might understand, 1 minus 1, well, it gives you 0. So if you put a green square with the red square, fill out, just as they did before with the blue square. So now we're left with minus 5 squared minus 4. We're still left with minus 4 squared. We just like simplified a little bit the problem. So what do we do next? And then this again looks a lot like what al-Khwarizmi does. He just does it with the minus 10x on the other side, so as a positive quantity. But we can still deal with it as a negative quantity. So what we're going to do is put this. We know that the red squares or the hash squares and the full squares, they cancel out with one another, like minus 1 and plus 1. So what we do is we put in the bottom right corner there. And what happens is that we get 9. So we're left with this shape here. And what we want to do is either form a square or a rectangle. So we can analyze it a little bit. We know that we had, 4 negative units, right? So the side here measure is 2. And since this before it was x minus 5, in this part here is x minus 7. This is also x minus 7 for the same reason. And so what you can notice is that this rectangle here, we can put it on the right side of the bigger rectangle. So we have this. And finally, you end up with x minus 7 by x minus 3. And you can see the original square of x by x. Again, this is a little bit funky because by putting the 10x on the other side, the equation is equal to 0. So we have to ask ourselves, what are the possible values of x or the roots for them to be equal to 0? Well, it either has to be 7 or 3. So this would be how you could adapt al-Khwarizmi's thinking or his method of thinking about algebra in today's mathematics using negative numbers. And it's quite convoluted, of course, because, we have squares with negative area. And so I would leave the question up in the air, and maybe someone in the Q&A has an idea as to what does that represent, right? If the square has an area that is negative, what's the measure of one side? And so that would conclude my talk. Thank you.
Thank you, Kevin. That was quite the introductory masterclass, and you introduced a lot of very, very complex concepts, but in a very, very in a way that I would like to think al-Khwarizmi would be very happy with. So thank you for doing that, and thank you, Pascal, for the historical context. So yeah, let's open it up. If anybody has any questions for either Pascal or Kevin, or a thought about what might be going on with square root of negative numbers, feel free to toss it right now. I know myself in high school math class, we were always taught that these were just imaginary numbers that were without representation. That really brainwashed me, and I know it brainwashed a lot of people for a long time. They were just sort of like useful little tools to balance out equations, but the idea that there is actually a susceptibility to intelligibility is a very, very exciting concept. And the fact that al-Khwarizmi's work was pointing us in that direction and is even opening up the door to really understanding that in a more perfect way is really cool. So if anybody has a thought or a question, go for it. a lot of very big ideas that require some chewing upon. I'd ask you though, Kevin, is there any work you would recommend for people who want to really understand al-Khwarizmi and imaginary numbers, especially, but al-Khwarizmi more broadly and his method? Is there any work you'd recommend that people could read or study?
But I would say just go with al-Khwarizmi's book. And like I said, if we can put the PDF in the description of the video on YouTube and maybe send it by email to people, just and I think what I've wanted to do here is to just give the mindset required to approach his work. And then, like I said, the book is like a textbook, really, with and the later chapters are really like problems that go deeper and deeper in terms of difficulties. So just read the books. The explanation are quite, sometimes are kind of difficult, but if you really if you understand that he's talking about squares and rectangles, I mean, you just draw out on a piece of paper what he's actually saying and try to work through the problems that he's explaining and showing to you. And I think that's gonna help people a lot understand what he was actually doing here.
Yeah, that's great advice, and that's one thing that really, I think, caused me to flunk out of math class when I was younger.
Sure.
It was that nobody gave me that advice, but rather it just became symbolic memorization of these magical formulas that you're supposed to just stick in your memory banks and deploy like a computer, and without any reason of why is this true or what does this represent in the physical world. It really destroyed the passion. So what you've done by just reintroducing reality governing these numbers and quantities that we're using it's a breath of fresh air. So it's good, very good advice. Thank you. I see
The
Meredith.
bummer is that
Yeah.
Well, the bummer is that in school today we go right away with the symbolics, right? We go right away with the symbols and how to manipulate the symbols. And like a lot of teachers will actually start with numbers, but they will manipulate the numbers themselves and then say that you can do the same thing with the symbols. But it's quite rare to start actually with the geometry and work around with the squares and the rectangles, which is a lot more visual as a method, and I think a lot more intuitive. Right.
Absolutely. All right. We have a couple of people who have lined up to pose some questions to you guys. So Magdalena, go for it.
Yes. Hi, Kevin. So I was struck at first. This is just a kind of an observation, but I was struck at first how you I think the very first slide that you had with the numbers. Maybe you can pull it up again.
I mean, like the rectangular and the square number?
No, not even that one. The one before, where you just looked at numbers, 1 to 10 or something.
Oh, right.
Okay.
So I'm going to share my screen.
Yeah, that one. Yes, exactly. Is that how he portrayed numbers 1 to 10? Because it's a very unusual arrangement. Well, I shouldn't say unusual. It's a different arrangement of the dots than we use nowadays, right?
Oh, you mean like I put the triangle here and the left hand, right side?
Right.
Well, for the 7, 8, those
even 5, right? Even 5 or 3, we're doing not that way. Okay.
Well, I'm curious how you would, because if I remember correctly, you're an elementary teacher. Is that it? Right?
Yeah.
So how would you present them? Because these was more sorted to represent the square and the triangle numbers, and others
Well, a 6, I would do an array, right? I would do 3 dots and 3 dots.
Right.
nicely underneath each other, right? And the 8 is exactly the same, 4 dots and 4 dots.
Right.
So I was just wondering why, okay, he would arrange it that way. And then I thought it
Oh no,
shows growth. Okay.
That's me that did that.
Oh, I see. Okay.
Yeah.
Oh, this is you. Okay.
Yeah,
okay.
a better idea would be to, I guess, would have been to do it as you said, and make to represent it as Theodotus actually talked about in the passage that we read at the start.
Okay.
Which is that you have the square numbers or the rectangle numbers, right?
Yeah. Okay. Okay. Then I had another comment. Okay, because when I teach the kids two-digit by two-digit multiplication, I use squares. I use, like, if I do 12 times 13, I do 12 squares and 13, and then I divide it into 10 tens, right? Just to give them the idea of that you can do 10 times 10, and then you can do 2 times 3 and so forth to add it up.
Yes.
So yes, okay. Because I always find that if you have a visual representation of this, the kids catch on to it much faster.
Well, it's cool that you mentioned that, because there's actually a chapter in al-Khwarizmi's book which talk about a method of multiplication. The multiplication of, I think it's either chapter 13. I think it's chapter 13. It actually talks about how you would multiply, two-digit numbers, and this is coming after chapter 1 through 12. So he builds on the visual representation that he used. So he's actually saying you multiply your tens together. So you basically add your 2 squares. And by multiplying the tens with the units and the units with the tens, you have the rectangles.
Yeah.
But those rectangles are always going to be of the same size. So you multiply them by 2, and then you add all of them together, and you have the product, right?
Right.
So maybe this is something that you could investigate, because it's pretty much what he says in the book. Yeah. And I would say that's the most intuitive way to talk about it is start with, I would often say to my students, like, think about how a sheep herder would count his sheep when he has 200 sheep, right? He takes his rocks, puts them in a basket, but then at the end of the day, want to know how much sheep he has. He's not going to count all the rocks. So he disposes them in an orderly fashion. And the most orderly fashion to do that is a rectangle, and you multiply the number of rows by the number of lines, right?
Exactly. Yes. Then lately I have found a few interesting ways of showing multiplication also, and I think it comes from India, okay, and China, I believe also, where they're using lines, drawing on piece of paper, but I have to investigate that further, because I was
like diagonal lines,
diagonal lines and horizontal lines and vertical lines.
Right. I don't know if I know this method, but I've seen, I think it's the Italians who have a similar method where they have a square, they put the numbers on top and on the left side. And I don't remember exactly, but they multiply in diagonal and then add things, and it works pretty well.
And it works every time.
Yeah.
I know.
Yeah, we have this tendency I don't know if it's in the West, but we have this tendency to think that, like the division by brackets, that's how you do the division, and the multiplication, that's how you do it.
Yeah.
And that's how everyone does it around the world. But there's actually a lot of methods.
Yes, exactly. And I think that shows a little bit of the arrogance on our side, okay, to not accept the methods of other cultures who do it perfectly fine also.
Sure, and I believe that actually, if you want to really make sure that your students really master the subject, go and find how other nations do it, right?
Yes.
Same thing as, when you want to learn the numbering system. We use the base 10 system, but when you do additions and multiplications, you take 8 plus 6, there you go over 10, so you make a 1 over there, but why the 1? Well, when you go and work with base 12 or 16 or 60 numbers and you try to do the additions or the other operations, you develop this understanding a lot more in the children.
Right. Okay, that's it, what I had. Thank you.
Thank you.
Cool. Meredith, did you have a question still in your mind? Oh, everyone's on mute by default.
Yes, thank you. Yes, curious about, I know we can't really know in the 12th century, 13th century, exactly what these distinctions were within Islam, within the religion itself, but just wondering if he could have been seen as a Sufi, an outlier, or as mainstream Islam. I just wonder if there's any coloration or tone that either of these two people that were giving these great lectures might want to add about his belief system or where he derived his beliefs about reality. I mean, where was it from the Greeks? Was it from Judaism? Because obviously there was this huge melting pot of influences. So just curious if either person wants to comment on that.
I'm not sure if Pascal, you want to add something, but as far as al-Khwarizmi goes, like I said, we don't know much about him apart from what he wrote and actually what what we received from him throughout the ages, because we lost a lot. What is cool about, and Pascal can go into more detail about this, but what is cool about the Islamic Golden Age is that they really went a long distance, pun intended, to gather knowledge from all around the world and throughout the ages. And I would say that's where it anchors into Islam, as some quotes from the Hadith that Pascal talked about.
Yes, right.
But other than that, I can't really talk much more about the theology of al-Khwarizmi. But maybe Pascal has some thoughts.
Yeah, thank you.
I'm not sure. I don't know. It's hard to tell because the knowledge was coming from everywhere, like we said, and different people. Like I had a slide on that, but people who worked at the House of Wisdom were also from different religions. So
yes,
it's it doesn't mean we could just go by the Abdid. Maybe it's the Sunnis. I don't know. Like who was the major player at the time or the in majority, but it's not clear because they were inviting people from all over the place to actually come and work at the House of Wisdom. So no, I wouldn't really risk myself in trying to tell because we don't know. Yeah, I don't know. I haven't found anything on that.
That's really, it was this just amalgamation of all this wisdom coming from so many different sources.
Yeah, and contrary to what people might think, it was really this ecumenical effort to actually get all the knowledge, like the quotes I gave from the hadiths, and there's more in the Quran, but I didn't want to flood people with quotes, but there's more and more. This very well-known quote: search for knowledge, even though even as far as China is really like that's the end of the Asian continent, but also opposite, but that denotes that it wasn't a question of categorizing people as, they're the good guys or the bad guys, or what religion can we go along these guys, maybe not. So it was a much broader effort, and that's something that we tend to forget, or that we're really told about.
That's right. Yeah.
Yeah.
Thank you. That was so lovely what you said. I just loved it. And your visuals were incredible.
Great, thanks.
Sort of a follow-up question. I don't know if either of you guys know roughly when Sunniism emerged, and my mother is asking a question here in the chat. When do either of you guys have an idea when there was when the split between Sunniism and Sufism split?
Oh, that's a hard one. I'm not exactly sure, but also it's I had a hard time sometimes, and Kevin can tell you, we were working together on this presentation. I was like, who's that guy? Oh my God, they all have the same name. How do I figure this thing out? And okay, there's somebody else who happened to have the same name, but they're not in the same place at the same time. It's hard. So sometimes also the dating, because it's not the same calendar as ours. It's the moon calendar, and it's from the Asia, so it's from I'm pretty sure I'm mistaken on that one. I think it's 622, the Asia, the year the zero of the Muslim calendar, or Muslim era, and so the Sunnis have
I asked Sunnis, but I really meant to
around
say.
six. Oh,
sorry. Yeah, finish your thought, and then I have a correction.
The Sunnis and Shia, I think it's around the year 660, but I might be off by a little. But it's on that. It's after Mohammed established Islam, and there were some fights between Mecca and all that, and after the death of the Prophet. There were internal fights, also civil wars. So it was a rough beginning. But I would say 660 Sunnis and Shia. That's kind of like the year around there, the split between those two. But Shia, I don't want to go too much into it. But it's really the split is between those that say that they bring forward the religion by Muhammad, who's the successor. So in terms in the Western side we would say like the Pope, and eventually we had two popes. Well, they kind of had the same thing on their side. So who's the legitimate successor to the Prophet? Some was Ali. They went with Shia. That's what created the Shia faction in Islam. So, but yeah, without going into much detail, there were more splits and fights. Yeah.
Thank you. Thank you very much. And I even though the word Sufi was drawn up there by myself and my mother, I think my mother meant to ask the question, when did the Sunni Shia split happen, which you intuited correctly. So thank you.
Thank you.
Yeah. And Jerry has a question.
Yes. Just want to thank Kevin and Pascal for that discussion, because it's an area I really don't know enough about, the whole Islamic Renaissance, both in terms of the science, the mathematics, but also in terms of history. So I just wanted to thank you for that. I have a comment, and then I have a question. Comment, kind of a weird comment, but when Madeline was asking the question and you pulled up that slide, Kevin, of 1, 2, 3, 4 to 10, the thing I noticed the picture you had of 10 was the one dot, and under that was a line of two dots, and underlying that was a lot of three dots, and underlying a lot, four dots. If you look at the slide Pascal had up from the School of Athens, and you had the picture of Pythagoras, where he's looking at a book and he's copying, it's the same thing there. 1 + 2 + 3 + 4, and he's got under that a line and 10. So
that's right.
It's interesting. There's a connection somehow between Pythagoras and Kevin, I think. But and Madeline too. So my question is the idea of negative numbers, because I always had a problem with it. And the way I figured it out myself, or the way that it works for me, is I think of direction, that positive is one direction, and I think of negative numbers as going in the opposite direction. That's just how it works for me. But I was wondering, oh yeah, there's the picture there, Pascal.
Mm-hmm.
I was wondering if you could comment on that, the idea of negative numbers and in terms of direction. That was my question.
Right. So, I work as what I do as work is basically writing textbook, right? It's not that, but the most simplest way to explain what I do. And lately, we've been one of my coworkers has been working on the numbers, right? Like adding negative numbers with positive numbers and negative with negatives. So we're actually like brainstorming about this idea. So it's cool that you bring the subject up. Yes, I think that directionality is one way to think about it, and it's quite effective. Let's say that, often what people will do is that they will represent numbers on a numbered line. And so if you have 5 minus 6, well, the numbered line is always as itself a direction, right? So you go from negative infinity to positive infinity. So if you start at the position 6 and you remove 8, then you're going to go on the opposite direction that the number line is going, so that you would go on the left side, and then where you end up is the result of the addition, right? It gets a little bit more complicated when you talk about multiplication and division. Yeah, it's basically, as far as addition and subtraction goes, the direction is a nice way to look about it. To think about it. I would say that from what I've studied also in as far as the origin of negative numbers go, from what I can tell, it comes mostly from India and China. And I think that one of the first way they were thinking about it is again from a physical sense, right? Well, a physical sense, because they were using money and debt to think about it. So they would say stuff like money plus money equals money, right? And then money plus debt, but when the money is greater, gives you money. But if you have money and you add debt to it, which is greater than the money you have, then you're left with debt, right? And debt plus debt equals debt, right? So they will think about it in those terms, and then you transpose that to the addition and subtraction and multiplication and division of positive and negative numbers, and you can make sense of it. And to go a little bit further, I would say that that's the kind of logic that I try to use when I presented the famous red square that is of negative area, right? So instead of working with money and debt, I think of it with and now it's a little bit more metaphysical, right? But it's a space, so an area, and counter space. So if you have space and you put them together, well, you have a greater space. But if you have a space of a certain amount, then you add to that a counter space, right? Well, you end up with nothing, right? And so I think this is, well, a cool way to look at it. And, this is where you end up in complex numbers, because you end up with areas of negative, geometrical forms in two-dimensional space with negative area. And, well, you have to have this idea of counter space, because if you have a square that's whose area is -1, then its side cannot be 1, because the area of that square would be 1. 1 times 1 is 1. And the side of that square can neither be -1, because -1 times -1 gives you 1. And it cannot be -1 by 1, because then it wouldn't be a square, right? So then you're left with the imaginary number, the square root of -1, sorry. So, yeah, it's I think the direction is a nice way to think about it, but then again, you can think about it in terms of money.
I admit that I'm with you on the degree that we talk about the negative numbers from the standpoint of money and debt. I'm cool with that. But I gotta admit, as soon as we get into multiplying negative numbers and dealing with spatial area, I do fall off the trail of your line of thinking. So maybe it's something I just have to keep on chewing on.
Well,
it's challenging.
I just didn't go into it, but the way to
Yeah.
think about it is to think about multiplication as a repeating, a repetitive addition, right? So let's say you have 2 times 5, then you can think about it as 5 plus 5s, or 2 plus 2 plus 2 plus 2 plus 2, right? And so when you bring negative numbers into that process, then you can make more sense about the multiplication of positive and negative numbers. But it's like I said at the beginning, we're at work, we're actually working on this, and it's not the most easiest of things to vulgarize, to talk about, because it seems simple, but it's quite complicated, actually.
Yeah. We might have to get you to do like a little evening weekday masterclass for the inner initiates who want to go into deeper mysteries. Cool. Luke, are you still there?
Yes.
All right.
Kevin, so when you were reading al-Khwarizmi, did you find any examples? Like, what was he measuring in his time? Was he measuring, like in the idea that he was constructing something? Was he putting carpet? Was he doing like a deck? Like, what was his example that he was using? That he needed to figure this out? Like, maybe I missed it, but if you can elaborate on that.
Well, when I presented all the chapters of the last chapter actually talks about problems relating to mercantile transactions, right? So I don't remember exactly, but it's things like you have sometimes it's how do you call it, heritage, right? Or transactions. So you have 1 cow, 1/2 of something equals something else. So it's really focused on economics, because really Khalif al-Mamun really commissioned al-Khwarizmi to write that book for commerce, basically, to facilitate the settling of transactions. But you don't really get that sense throughout the book. It really comes at the end when he says, now we're going to look at economic example, right? but otherwise he's really into squares and rectangles and numbers. That's pretty much what he's doing. Yeah.
Did you tell me some weeks back that much of his work wasn't translated into the English editions, and like his metaphysical and philosophical material was sort of left out from the non-Arabic translations?
Yeah, so, and this happened a lot with, not only with al-Khwarizmi, but a lot of the translations of, Islamic books, is that they would condense sometimes what's written. So, like the book by Robert of Chester. So actually what we have is, well, the book that I have is, you have on one side the Latin translation of Robert of Chester, and then you have on the right side the English translation. So you're like 2 degrees removed from the original book. And they will often, and in the case of this book, they would condense or leave out parts, maybe sometimes because of philosophical or theological reasons, because it was Christians translating Muslims, so they didn't like how they would talk about God or whatever. But yeah, it's quite an incomplete translation. And when you look at, let's say, chapter 1, chapter 1, 2, and 3 that we looked in this presentation, it's this big, right? It's not even 1 page. And so I have a hard time believing that in al-Khwarizmi's original work, he would only spend like half a page talking about solving equations, right? Mm-hmm. Yeah, so that's a problem when studying this.
Mm-hmm. Even with Kepler's material, right? Like it took 400 plus years for his Harmonies of the Worlds to be translated into English out of Latin, and even then, it was only the last fifth because there were 5 books with his that were part of his Harmonies, and only book number 5 was published, I think, in the 50s, that you could access if you didn't read Latin, because all of his metaphysical and harmonic and philosophical material was deemed irrelevant and impractical, or that was the excuse given for not translating it, and only the hard astronomical material at the very end of the book was deemed useful for astronomy. So that's what they then justified in translating it. And it took up until 1991 for people to finally wait to read the other 4 books that gave you the real heart and soul of how he was thinking when he was, making his discoveries. So I guess that's a challenge implicitly for any Arabic speaker who's into translations out there, who has access to the full unredacted al-Khwarizmi, to please get working on this and give a gift to humanity. Pascal, I got a question regarding the houses of wisdom. What were the like, I know you were saying that there's Christians and Jews studying together in the House of Wisdom. Christians and Muslims studying together. Were there Jews as well studying in these houses? And what about Buddhists and Confucians from China? Were other cultural groups outside of the 3 big Abrahamic faiths working on astronomy and science?
Pretty sure, yes. There are some. Basically, it's interesting. Like the names, I was giving the names, and sometimes when their works were known to us in the Western world, well, we translated their names and give them like some more Latinized name, and you don't necessarily know. Sometimes I'd forgotten. Averroes was Ibn Rushd. It's not as close as Ibn Sina and Avicenna, but the same thing happened also to those that came to work at the House of Wisdom. So sometimes they seem to have an Arabic name, but they are Jewish translators. They are, Persian. So it's not always easy. At least for me, it wasn't easy, not knowing the language, the Arabic language, to spot them. But you have a lot of them, yeah, that were converging, because the Silk Road really, like when you look at the Middle East or Southwest Asia, we should say, really was the converging. All of the routes were, it was the hub. Everything was converging towards that place. Everybody had to go through. So yeah, it was really a meeting point of all of these cultures. So yeah. I don't have any examples right now, but I remember stumbling upon different authors and thinking they were Arab, but no, they were Jewish or of different faiths. Yeah.
Nick wrote the Husamov Scholars, Toledo, Spain, same thing. Nick, could you say a little something about what you just said there in the chat? Nick, you're on mute.
Hi, I'm sorry, Matt. And I misspelled. There's something called the House of Scholars in Toledo, which is where a great many churchmen and people who were multilingual, came from all over Europe, Christians, Jews, anybody, to study. And then they went back to their respective countries or church institutions, and whatever they learned in Toledo, they brought with them and spread it throughout Western Europe. And the Toledo stuff came in part from the House of Wisdom, from Baghdad, and other sources as well, throughout Western Europe. It was kept originally prior to the House of Scholars in Toledo, and I'm not sure what the original date of that would be, but they had the same amount of wisdom going even in the Dark Ages into the cloisters and the monasteries, Islamic knowledge, which was kept there. And then when there was a little bit more, I guess, freedom or openness about it, they had this congregation of scholars in Toledo. So there's a really quite a lovely Jewish temple in Toledo. It's not very big, but you can visit it. And then, of course, there were huge amounts of Arabs and Muslims, rather, in Toledo during those years. So the House of Scholars, again, it's like I'm probing back into ancient memory here, but it must have been around 1100, 1200 at least, when it was highly functional and spreading all this knowledge throughout the rest of Western Europe.
Mm-hmm. That's true. Exactly. You're right. And that's why I was, it's not sure when Baghdad was destroyed by the Mongols. Certainly we lost, a great deal of stuff, the library and all that. But a lot of these works were translated and shipped all across the caliphate. So that's true. Toledo was a center, Cordoba. When the caliphates had internal fights, the Humayyad with the Abbasid, there was a split, but so the knowledge was also maintained. The knowledge that had transpired from the caliphate before, it was still maintained. So yeah, that's an interesting point. Under Alfonso the Great in Spain, or Al-Andalus, there was this exchange of the three religion, and that's also very interesting to study. I didn't really go into that, because of time. But yeah, that's Al-Andalus would be also a very important subject to discuss eventually on its own.
Absolutely. I think there's a lot of wonderful leads here for future gold mining of ideas. And we're really overdue for a new network of houses of wisdom. And the House of Scholars is a fascinating thing. I didn't know too much. I didn't know anything about this. So this is a really, really cool and yet another cool lead. So thank you for bringing that up. We're reaching the end of our time allotment here this afternoon, so I just wanted to thank everybody for taking this edifying 2.5 hour period here to get to the roots of some big ideas. I really appreciate that little pun that you guys went with. We're gonna use this a lot. And Kevin, Pascal, you guys did great. Thank you so much for sharing your work. And next week, we're going to have Marty Seif, I believe, who's going to do something regarding some battles around the Soviet period against the Nazis and some key generals that have been wiped out of especially Western history books, who he's going to bring to the surface. So that'll be fun. So I hope everyone is able to make it next Sunday. And thank you all for taking this time today. Bye.
Thank you, gentlemen.
All right. Thanks. See ya.
Bye.
Thank you.
Thank you. Thanks.
Merci, merci.